Okay, ladies and gentlemen, you are welcome. In this video, we are going to look at the concept of Graham's law of diffusion, and we are going to start with example one. And ladies and gentlemen, don't forget to subscribe the video and also join our YouTube community for you to have more videos. I think, ladies and gentlemen, from the previous video, where we actually discuss about the Graham's law of diffusions with the mathematical derivation of the formula, you can see that we have different formula. And of course, I think if you can remember from the formula, the rates of the low step that the rate of diffusion is inversely proportional to the square root of the masses, or is inversely proportional to the square root of a mass of the substance. So let's say now we have gases, let's say we have two gases, and of course whenever we have proportionality, we introduce constant. So therefore now the rate of the diffusion is equal to K all over square root of the molecular mass of the gas. So we can write a formula from here to see that, okay, so the rate of the diffusion of gas A divided by, or gas 1 divided by the rate of the diffusion of gas 2 is equal to, so because it is actually inverse relationship, so the rate of the diffusion of gas 1 is the same thing as the inversely proportional to the square root of the mass of the gas A, and also the rate of the diffusion of gas 2 is also inversely proportional to the rate of the diffusion of gas 2. So it's inversely proportional to the square root of the mass of gas 2. So this is actually the first relationship where we have the rate of the diffusion is inversely proportional to the square root of the mass of that particular gas. So therefore, ladies and gentlemen, you should understand that in this law, that is Graham's law of diffusion, is the law that trying to show the relationship between the rate of the diffusion of gases and the molecular mass. And of course, the rate of the diffusion of gases is inversely proportional to the square root of their masses. So if we have two gases, at the end we are going to have a relationship where we are going to have the rate of the diffusion is inversely proportional to the mass of that particular gas. And of course, the rate of the diffusion of gas 2 is also inversely proportional to the molecular mass of that particular gas. So actually here we are given questions to answer, and I think let me just give all the formulas that we are going to work under this Graham's law of diffusion. So we also have a formula that shows the relationship between molecular mass and the density, or the Beaufort, the density of substance, or the Beaufort density. So therefore, the molecular mass is always 2 times the Beaufort density. So if you are given a density and you ask to calculate the molecular mass of a particular element, then you are going to multiply that Beaufort density times 2, and that will give you the molecular mass of that particular element or a particular gas. And also the rate of the diffusion itself, it also has a formula. So rate is the same thing as volume all over time. This is also another formula that shows the relationship between volume, the rate of the diffusion, and the time. So here we are given, the question says calculate the molar mass of a given gas whose diffusion rate is 2.92 times the diffusion of ammonia. So here we are talking about two gases. So we don't know the first gas because it is just stated as a gas. So let's assume the gas to be X. So therefore the rate of the diffusion of the gas, that's let me be using capital R as the rate of diffusion. So the rate of diffusion of gas X is 2.92, because it is 2.92 times the rate of the diffusion of ammonia. So therefore, if the rate of the diffusion of gas X is 2.92, so therefore, since the rate of the diffusion of ammonia is less than the rate of diffusion of gas X by 2.92, so that the rate of diffusion of ammonia is now going to be 1. The rate of diffusion of ammonia is going to be 1. Since from the statement, the rate of diffusion of gas X is 2.92 times the rate of diffusion of ammonia. So if the rate of diffusion of ammonia is 1, so therefore the rate of diffusion of the gas is equal to 1 times 2.92. So 1 times 2.92 will give us 2.92. That is the rate of diffusion of that particular gas. And of course, at the same time, we have the molecular mass of ammonia. Since we don't know gas X, but we know that we have to calculate the molar mass of ammonia in history. And of course, to calculate the molecular mass of ammonia, we need to know that the molecular mass of nitrogen is 14, the atomic mass of nitrogen is 14, and the atomic mass of hydrogen is 1. So therefore, here we are going to have ammonia. We have 1 nitrogen here, so we have 1 times 14 in brackets, and then plus we have 3 hydrogen, so we have 3 times, and the mass of hydrogen is 1. So therefore, we now have 1 times 2 is equal to 14, and then 3 times 1 we have 3, and this will give us 17 grams per mole. So this is actually the molecular mass of ammonia. So therefore, we are now going to use this formula to calculate the molecular mass of the gas. So therefore, now we are now going to set the rate of diffusion of gas X divided by the rate of diffusion of ammonia, which is equals to the molecular mass of ammonia divided by the square root of the molecular mass of gas X, which is actually the one that we are going to find out. So therefore, the rate of diffusion of X is equal to 2.92 divided by the rate of diffusion of ammonia, which is divided by 1, and therefore we now have the molecular mass of ammonia to be 17, and then divided by the molecular mass of gas X. So therefore, this divided by this is going to give us 2.92 divided by, so since here is a square, is actually a square root, so we can now remove the square root by squaring the both sides of the equation. So therefore, we are now going to square the both sides of the equation. So therefore, here we have the square of this, and then we have 17 divided by the molecular mass of X. So we are now going to make the molecular mass of X subject of the formula. So therefore, we now have 1 times 17, and then mx times this. So therefore, we now have mx times mx into 2.92 square, then we have is equal to 17 times 1. We are now going to divide this through by the equation. So we now have 2.92 square here, then divided by 2.92. Then we square this, so therefore this one will now cancel this, and we now have the molecular mass of X will be equals to 17 divided by 2.92 square. So therefore from here, you can take our calculator to get the molecular mass of X. So if you take this and divide this, and we divide it by the square of this, it's going to give us 2.0 grams per mole. So ladies and gentlemen, I want you to confirm the answer to see whether we are correct. So ladies and gentlemen, I think from these examples you can see how we are able to calculate the molecular mass of gas X, which found to be 2.0 grams per mole. So let's look at another example. So let's look at another example. So we have example 2 and example 3. So example 2 said that a sample of nitrogen and oxygen gases are in a container are in a container with a small hole leading to another empty container. Which of the gas diffuse first? So here we are talking about two gases, nitrogen and oxygen. So the question is, which of the gas will diffuse or diffuse first? So I think, ladies and gentlemen, if you could remember, the rate of diffusion is inversely proportional to the square root of the molecular mass of the gas. So now, what does that mean? It means that the higher the higher the higher the molecular mass, the lower the rate of the diffusion. And the lower the molecular mass, the higher the rate of the diffusion, because it is inverse relationship. So whenever we are talking about inverse relationship, and we're talking about two gases, so the one that have the higher molecular mass will have lower rate of diffusion, and the one with lower molecular mass will have the higher rate of diffusion. So therefore, the lower the molecular mass, the higher the rate of the diffusion. And the higher the molecular mass, the lower the rate of the diffusion, because of the same matter relationship. So therefore, now you have two gases. You have nitrogen gas and you have oxygen gas. So the question is, between these two gases, all of the two gases diffuses that lead to the empty container. But among these two gases, which one diffuse or effuse first? So we are going to know that based on the molecular weight. So the one that have the lower molecular weight will diffuse faster, or will diffuse fast, followed by the one with the higher molecular mass. So here we are talking about two gases. So of course the molar mass of nitrogen is 14 and the molar mass of oxygen is 16. So we are talking about these two gases. So we are now going to calculate the molar mass of these two gases. So we have 2 nitrogen times 14, and this will give us 24 grams per mole. And we have oxygen. And how many oxygen do we have here? We have 2 oxygen. So we have 2 times 16, and this will give us 32 grams per mole. And then the next thing now, we are now going to look at this molar mass of two gases. So between these two gases, which one have the lower molecular weight? So the one with the lower molecular weight in this case is nitrogen. So therefore, nitrogen will effuse faster, or will effuse fast. So the answer is the nitrogen gas will effuse fast because of its lower molecular mass, followed by the oxygen gas. So this is how to answer this question. So then let's move to question 3. So we have two gases also here. There we have 200 centimeter cube of a gaseous hydrocarbon which diffuses through a porous port in 452 seconds. Then the same volume of hydrogen under the same condition diffuses in 117 seconds. So I think, ladies and gentlemen, if you could remember from the starting point of this lecture, I told you that there is a relationship between rate of diffusion, the volume, and the time. So therefore, now the rate of diffusion can now be volume all over time. And of course, so here we are talking about two guys. So let's say the rate of diffusion of hydrocarbon and also the rate of diffusion of hydrogen. So we are now going to say volume of hydrogen divided by the time. So you see, I think you can see clearly here, the volume of the hydrocarbon is already given as 300 centimeter cube. So therefore here we have 300 centimeter cube. And the time is 452. So we have 300 divided by 452. And of course, the same volume of hydrogen. So the same volume, it means that the same volume with that of the hydrocarbon. So the hydrocarbon is 300 centimeter cube. So the same volume of hydrogen under the same condition diffuses in 117 seconds. So what does that mean? It means they maintain the same volume, which is also 300 centimeter cube. And of course, the time is 117 seconds. This one also in seconds. So therefore, we are now going to take our calculator and get the answer. So if we now take 300, and we divide it 300 divided by 452, this one will give us 0.664. And then if we take that of the rate of diffusion of hydrogen gas, is now going to be 300 divided by 117. And this will give us 2.564. So these are the two rate of diffusion. So I think since we already have the rate of diffusion, so the next thing is calculate the molar mass of the hydrocarbon. So therefore now we are now going to say the rate of diffusion of hydrogen gas divided by the rate of diffusion of hydrocarbon is equal to square root of molecular mass of hydrocarbon divided by the molecular mass of hydrogen gas. So the rate of diffusion of hydrogen, we have it as 2.564 divided by the rate of diffusion of hydrogen gas, so the hydrocarbon, is equal to 0.664. And we are now going to say it's equal to square root of the molecular mass of hydrocarbon, which is unknown. The molecular mass of hydrocarbon divided by the molecular mass of hydrogen. And you know that the mass of hydrogen is 1. And we have 2 hydrogen here. So therefore, we now have 2 times 1, making 2 gram per mole. So therefore, here we have gram per mole as a molar mass of hydrogen. So therefore, the next thing now is to check our calculator and divide 2.564 divided by 0.664. And this will give us 3.8616. 3.862. Therefore, here we have 3.86. We have 8.62, and is equal to square root of the molecular mass of hydrocarbon divided by the molecular mass of hydrogen gas, which is here, is going to be 2. So what we are trying to get is actually the molar mass of this. So we are going to square this to clear the square root here. So therefore, we are now going to have the square root of 8.862, the square root of 3.862 is going to be 14.91. So therefore now we have the molecular mass of hydrocarbon all over 2. So we are now going to cross multiply. So this one time this and this one time this. So we are going to have the molecular mass of hydrogen gas to be 14.91 times 2. So if you multiply everything here, the molecular mass is now going to be, if you approximate, it's going to be 30 gram per mole. So this is the answer for this question. So ladies and gentlemen, please, if you watch this video, don't forget to subscribe and join to my YouTube community so that you will be able to watch all other available videos in the YouTube channel. Thank you very much, ladies and gentlemen. And after you watch this video, I'm also going to give you some questions to try. Thank you very much and see you next in my next video. Please don't forget to subscribe.